Hey, come check out these parts. They're both MOSFETs, but one is made with silicon and the other is made with silicon carbide. Can you tell the difference? Well, in this video, we cover what silicon carbide transistors are, how they are different from traditional silicon, applications for them, and briefly cover a unique simulation tool from onsemi. My name is James, and welcome back to Workbench Wednesdays. Let's go review. This video is sponsored by onsemi. Their elite SiC products include silicon carbide diodes, MOSFETs, and modules that contain a hybrid of traditional transistors along with silicon carbide-based devices. There are three high-level applications for silicon carbide, or SiC, or SiC power devices. Those are solar, energy storage, and electric vehicles. And more specifically, these devices are used in the power converters found in those. Historically, IGBTs were found in these applications because they could tolerate the high voltages. However, their switching speeds are limited to relatively slow speeds. Now, when I say high voltage, let's use a solar example to find out what that means. A solar string inverter ties multiple panels together to a boost converter that steps up the variable solar voltage into a stable DC bus like 1000 to 1500 volts. Voltages this high reduce the ohmic losses in this system. The DC to AC inverter then converts that bus to AC voltages suitable for a load or going to the grid. In general, regardless of the topology used in these stages, the higher the switching frequency, the smaller the capacitors and magnetics can be. Higher voltage means better efficiency, and higher frequency means smaller passives. Both contribute to an overall lower cost design. Next, let's look at how a SiC MOSFET compares to the traditional devices made with element number 14. Silicon carbide is a hard chemical compound made of silicon and carbon. Well, I mean, the name gives that away, but the important part is that it is a semiconductor material, and when you think semiconductors, you should think diodes and transistors. A traditional power MOSFET has a silicon substrate, some doped layers, and a thin insulation material to form the gate. Oh, and electrodes for the source and drain. When operated as a switch, three things really matter. How much voltage can you put across the drain and source when the switch is off? Also, how much resistance is there between the drain and source when the switch is on? Last, how fast can we turn it on and off? In a power switch, the thicker the drift layer, the higher its breakdown voltage. However, that thickness also dominates the on resistance. And depending on the materials, switching losses can occur because of how the FET turns on and off. And yes, I know there's variations and different ways to construct them. But sticking with the planar designs, let's compare to a silicon carbide MOSFET. It's essentially the same stack-up. The critical difference is that the substrate is now silicon carbide, or SiC. Imagine that. Silicon carbide is a wide bandgap material. Compared to silicon, it has a 10 times higher dielectric breakdown field strength, 2 times higher electron saturation velocity, 3 times higher energy bandgap, and 3 times higher thermal conductivity. Those impressive numbers mean a SiC device has higher breakdown voltages with an even thinner substrate compared to a traditional MOSFET. And then, with that thinner substrate, there is less resistance in the drift layer when conducting. Also, the smaller devices have less junction capacitance. That, along with the higher electron drift velocity, means a SiC transistor can be switched on and off faster. There can be thermal benefits to silicon carbide as well. So it is a switching device that can withstand over 1000 volts with an on resistance down to the tens of milliohms and can operate in the 200 to 400 kilohertz range. That's cool. So what does it take to use them? Turns out, in a schematic, it is really easy to change from a silicon to silicon carbide transistor, but there are a few things we need to realize in practice. Typical silicon MOSFETs fully turn on with 10 to 15 volts from gate to source, while SiC needs up to 20 volts. Also, when turning off the FET, silicon turns off before 0 volts, while silicon carbide needs a slightly negative voltage. And while that might seem troublesome, fortunately, there are gate drivers available for SiC, like this one from onsemi, which uses a charge pump to produce a negative voltage for turnoff. For the question of cost, there is not a simple answer. Individual silicon carbide devices generally cost more than a MOSFET, and definitely more than an IGBT. But when you consider the total system cost, especially in a new or redesign, silicon carbide can be on the same level or even more affordable. Remember, they generate less heat, so you have less heat sinking. They operate at a higher voltage so you can have smaller bus bars. Also, they can operate at higher frequencies so the passives can be smaller. All of these aspects can add up to a cost savings that might offset the price of the individual transistors. Since you cannot breadboard a 25 kilowatt power converter, well, at least not more than once, power engineers extensively use simulation. And for simulation, you need good models. So let's talk about those next. When you think simulation, you might think of something like the Falstead or other SPICE-based simulators. And SPICE is great for low-level analysis, but it is limited. In power electronics, you need to simulate at a system level and include domains other than electrical, like magnetic and thermal. And you're especially interested in the switching losses of the MOSFETs themselves. For this work, one such tool is called Plex. It is a sophisticated platform that can do multi-domain modeling. And then for system-level simulations, you can use onsemi's Elite Power Simulator tool, which is powered by Plex. This one takes a step-by-step approach. For example, within your industry, you select your design's converter topology. Then you set some parameters for voltage and power. Decide if you want to model discrete MOSFETs or a module. And then select the specific device you want to simulate with. For the loss model of the transistor, you can use a nominal best or worst case. But for onsemi's silicon carbide parts, they do things a little different from other companies. Typically, when component manufacturers, and not just transistor makers, create models for their parts, they do it by measuring a small number of actual components in a small number of cases. Then they build a math model based on that limited data set. The SiC models from onsemi are based on the physical device's topology and packaging parasitics. The result is what they call a scalable model. But wait, there's more. Your test setup also affects the model. So onsemi also has a tool called the Self-Service Plex Model Generator. It combines the physical device model with your detailed test setup parameters to generate an application-specific model for Plex simulators. By the way, it takes on the order of tens of minutes for onsemi to generate those models and send them to you, at least when I saw it. But the process is automated. Once done, you can download them and conveniently use those models in the Elite Power Simulator. Next, you set your switching frequency and leakage inductance. And last, you give the simulator your thermal solutions parameters. Once the simulation is done, you can look at the switching and conduction losses, junction temperatures, expected currents, and more. A summary page provides all of the critical details that you can save or print. There is quite a bit to generating the models and using the tools, but if you plan to work with SiC devices in your designs, I highly recommend taking the time to understand how you can use onsemi's models in your simulations. Follow the links below to the show notes on the Element 14 community. There I place links to the web-based tools I showed and some application notes to help you get started with onsemi's SiC devices. In review, a silicon carbide MOSFET is a MOSFET with some unique capabilities. When working with multi-kilowatt or megawatt converters, their high breakdown voltage, low RDS on, and fast switching can mean more efficiency and less overall cost for a system when used in a high power converter. Check out the design tools that onsemi provides for their components so that you can fully evaluate how they would work in your design. Hey, thanks for watching. Do not forget that the Element 14 community is the best place to ask electronics questions. If you want to see more E14 videos, tap or click the things on the screen below me. For now, it is time for me to get back to megawatt power conversions on my electronics workbench.